Euclidean rhythms are all the rage at the moment. But what actually are they, and how would we go about making our own Euclidean rhythm calculator? To do this, we need to talk about maximal evenness. Let's say we have 8 hours in our day, and we have 2 friends to meet. In order to spend the maximum amount of time with each friend, we have to meet our first friend in hour 1 and our second friend in hour 5. We then have 4 hours for each friend. Now let's say we have 4 friends to meet. Then we'd meet the first friend in hour 1, the second in hour 3, the third in hour 5, and the final friend in hour 7. That way we get to spend 2 hours with each friend. The situation gets a little more complicated if we have 3 friends to meet. Let's say all our friends insist on meeting only on the hour, not at 20 past or quarter past, just on the hour. So in this case, we could spend 3 hours with 2 friends and 2 hours with the other friend, meeting our first friend at hour 1, our second friend at hour 4, and our third friend at hour 7. Or we could meet the second friend at hour 3, and the third friend at hour 6. Or we could meet the second friend at hour 4, and the third friend at hour 6. So how can we apply this to music? Well, let's say if we have 8 steps in our sequencer, and we want 3 hits of a kick drum, but we want them spaced out as evenly as possible, then we'd have a rhythm sort of like this: hit, rest, rest, hit, rest, rest, hit, rest. So let's call a hit 1 and a rest 0. So we'd have a list like this: 1 0 0 1 0 0 1 0. This is how it looks on a stave. So we've got the hit, rest, rest, hit, rest, rest, hit, rest, and on a MIDI roll like this. And this is how it sounds. The spacing between each hit is as even as it could be. We have maximal evenness. If you're wondering what Euclid has to do with all of this, the rhythms are only maximally even when they are Euclidean rhythms, and we can use a process derived from the Euclidean algorithm to calculate a set of hits and rests, or ones and zeros. So for each step, we multiply it by the number of hits. So we're on step 1, we times it by the number of hits, which let's say is 3, so we get 3. Now we divide this by the number of steps, and we ignore everything after the decimal place. So 3 divided by 8 is 0 point something, so we just take 0. Now we compare this truncated divisor, as it's called. We compare this truncated divisor to the one from the previous step. Now if there's a change, we output a 1, and if there's no change, we output a 0. If it's the first step, we always output 0. And then finally, we take the list or the column and we rotate it down or to the right by 1, so that the final 1 is the first item. And the final number should always be a 1. So let's do this for 8 steps and 3 hits. So we've got our step numbers from 1 to 8, then we times it by the number of hits, which is 3, and then we divide those by 8, and we ignore everything after the decimal place, and then we look to see if there's a change from one to the next. So from 0 to 1, that's a change, so we put a 1. From 1 to 2, that's a change, so we put a 1 there, and 2 to 3 is a change, so we put 1 there. And then we rotate it so that that final 1 is the first element of the list or the column. And we end up with that. So let's do the same thing with 13 steps and 5 hits. And then we get something like this. And you can pause the video if you want to see how I work this out. And that's how this looks on a MIDI roll. And on a stave, like that. And this is how it sounds. Now with 12 steps and 7 hits, we get this: 1 0 1 0 1 0 1 1 0 1 0 1. So as a rhythm, it is like this, it looks like this on a MIDI roll, on a stave, and it sounds like this. But how about if we apply this maximally even set, not to a rhythm, but to a set of pitches? So we've got 12 steps, 7 hits, and 0 rotation. So let's take the notes of the chromatic scale from 1 to 12. And so if we take the notes where there's a 1, and we ignore the notes where there's a 0. So if we do that, we end up with this, C, D, E, F sharp, G, A, B, which happens to be the Lydian mode. Interesting. So how about if we rotate this by 2? We end up with the Mixolydian. By 4, the Aeolian. By 6, Locrian. By 7, Ionian. 9, Dorian. And 11, or -1, Phrygian. So these maximally even sets appear in music and in nature, sort of everywhere. It's kind of fascinating, really. Now, if we have 12 steps and 5 hits, we have this rhythm. So hit, rest, rest, hit, rest, hit, rest, rest, hit, rest, hit, rest. It looks like this on a stave. And if we apply it to pitches, we end up with the pentatonic scale. So I'm going to show you 3 really simple ways of making a Euclidean rhythm generator in Max. The first thing I'll do is I'll create 3 integer objects by pressing I. I'll comment that with steps, Shift Enter, Command J to snap, and then I'll duplicate that with Command D, and again, so 1 for hits, Command J, and 1 for rotation, Command J. Now I'll pack these into a list so that whenever any of these numbers changes, the list is output again. And then I'll unpack them so I can access each element of the list individually. Now, I know I'm going to need an Uzi object to output all the steps of the sequence. If I send an integer into the left inlet, then that's the same as entering an integer into the right out inlet and sending a bang to the left. So the simplest way is just sending an integer to the left inlet. And then I'm going to need something to collect all these indices coming out of the right outlet here. And to collect all of those, I'm going to need the ZL group object. And the ZL group object needs to know how many things it's collecting before it starts receiving them. So in order to make sure that it receives that number first, I'll use the trigger object with 2 integers being output. So the second thing that's going to be output is this number going into the Uzi object, but first is this integer telling the ZL group object how many items to collect. So let's just observe that with a message box now. So I'll put 8 steps in there, and so I've got 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, so I'm now going to need to multiply each element of this list by the number of hits. So to do that, I'm going to need the vexpert object to multiply every element in the list by another number. And that second number is going to remain constant, so I'll need to use scalar mode. So I'll use the attribute scalar mode 1. So I'll send in the list to the left inlet, and I'll send the second outlet of the unpack object into the right inlet of the vexpert object. So let's observe that now with the message box. So 8 and let's say 3. So we've got, 3, 6, 9, 12, 15, 18, 21, 24. And just to remind you of how we get there, let's do that. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And then each element of that list is multiplied by 3, which is the number of hits we have. Okay, now I need to divide each element of this list by the number of steps, and then I need to ignore everything after the decimal point. So I'll use another vexpr object. So the inlet 1 divided by inlet 2, and I'm using integers to get rid of any of the decimal places. And again, I'm using scalar mode because I'm dividing by a constant, which is the number of steps. And I can use the integer from this trigger object. So let's observe this now. I'm expecting to see 3 divided by 8, which is 0 point something. So 0, 0, 1, because 9 divided by 8 is 1.125, but just 1. And then 1, 1, 2, 2, and 3. So let's see if that's right. 0, 0, 1, 1, 1, 2, 2, 3. Good. Okay, now I think I'm going to want to save some space. So rather than having 2 vexpr objects, I can actually just use 1. So I'll use some brackets. I'll put this in a bracket, and then I'll divide it by a third inlet. And I'll just replace that with that. So let's just check that's the same. Yep, it's the same. Good. Okay, now I need to compare this list with another kind of imaginary list, because this first element is always going to be a 0. So what I need to obtain somehow is a list that looks something like this. So basically I'm knocking off the final element and I'm adding a 0 before the first element. But first I need to duplicate the lists. And to do that, I'll use a trigger object. And I'll use 2 lists, so TLL. So first, this right outlet will be output, and I'll prepend that with a 0. And to take off that final 3, I'll use not the ZL slice, but the ZL eSILs, so that the final number will be output the right outlet, and all the previous numbers will be output the left outlet. So let's take a look at that list now, and let's also take a look at what's coming out of the right outlet. Yeah. So we've got 0, 0, 0, 1, 1, 1, 2, 2, which is exactly what we want. Yeah, so now we can compare these lists. And by compare, I mean we minus one list from the other. And to do that, I'm going to use the vexpr object again. So list 1 minus list 2. And just to be on the safe side, I'm going to check if this is equal to 1. So if it's a 1, it will 1 is equal to 1, so this will output 1. If it's 0, then 0 does not equal 1, so this will output a 0. So let's observe that with a message box. Zero, 0, 1, 0, 0, 1, 0, 1. Okay, cool. So now, finally, I just need to rotate it. And to do that, I'll use the ZL rotate, or ZL rot. And so I'll send it that. And I'm just going to take this third outlet from the unpack object, +1, and I'll send it to that ZL rotate. And let's observe that list with the message box and see if we end up with the correct list. So we're expecting 100, 100, 10, and that's exactly what we get. Let's change the rotation. Perfect. Okay, so if we have 12 steps and 7 hits, and the 0 rotation, we'll get, so if we call that C sharp 0, so we get C, D, E, F sharp, G, A, B. So that's the Lydian mode. So this next method is very similar. The only difference is that I'm going to be grouping the elements into a list at a later stage. So we'll also use an USI object, and we'll also use a ZL group object, but it will be lower down in the list. So we need to, this ZL group object needs to know how many items to group together. So we'll need the trigger object to make sure it receives that information first. So that will be going all the way down there. And then the second order output will go into the first inlet of the USI object. And we're interested in the kind of step count, or the current index coming from that USI object. So we'll multiply that index by the number of hits, and the number of hits comes from the second or element 2 of the unpack object. Now we need to divide that by the number of steps, which we can also get from this first order output from the trigger object. Is that right? Yeah. Now we need to compare the current. So this is what's coming out of here is called the truncated divisor. So we need to compare the truncated divisor on this step to the truncated divisor from the previous step. And remember, on the first element, we're comparing it to 0. So we need to use a minus object to do the comparison. And so the first element, we'll subtract 0 from the first element. So we'll need to add a 0 from this trigger object. And then we'll need another trigger object with 2 integers being output successively, so that the truncated divisor from the current step will be subtracted from the truncated divisor from the next step. So this second order outlet will go to the cold inlet of the subtraction object. And then finally, we'll group all those together with the ZL group, and then we'll rotate them again. Then add 1 to that rotation, as always. And let's see if we get the right sort of list with 8 and 3. Let's see. 100, 100, 10. Perfect. So that's method 2. My final method is going to be using the JavaScript object, or the JS object in Max. So to do this, you'll have to save your patcher, and then double click, type in JS, JS and create a new JavaScript file. I'll call this Euclidean list.js. Now, if I double click that, I'll get the inbuilt Max text editor. I don't really want this, so I'll click Control S and I'll call this Euclidean list.js and press save, close it. And if I double click it again, it will open in my text editor of choice, which is brackets for the time being. Now, yeah, so I want one inlet. So to do that, I need inlets equals 1. I want one outlet to output my final list, and I'll turn on auto watch. Now, I'm going to send in the list, a list of 3 items, which will have the number of steps, the number of hits, and the rotation number. So to send it a list, I'll use the function list, which is inbuilt in Max. Max knows what to do with that, and I'll create a variable vals, which is going to be equal to this other inbuilt function in Max, array from args, and yeah, I'll give that an argument of arguments. Now vals will be output from this list. So let's just check that. So we'll output the list here. So outlet 0 vals. So I'll save that, go back into Max, and if I send the output of that pack object into the JS object, I should see all the numbers I have here. So let's try that. No, probably need to compile it. So I'll create a compile message. Okay, cool. So 830, perfect. Okay, so I'll go back into brackets and continue editing. So we want a variable called steps, which is going to be equal to the first element of the vals variable. So we start counting from 0. And we want a variable called hits, which is the second element, and rotation, which is the third element. Now we also want to create an empty list to send out, which is going to have our final list of 1s and 0s. So I'll call that variable A, and I'll make that equal to an empty list. So for every step, we want to multiply it by the number of hits and then get the truncated divisor, compare it to the previous number, and output the list that way. So I'll be using a for loop for that. So for var I equals start counting from 1, same as the Uzi object. And when that's less than or equal to the number of steps, we'll stop, and then we'll increment by 1 every time. So we'll have a variable x and a variable y. So x will be so first we'll do the step count times by the number of hits. But then we'll divide this by the number of steps. But we want that as an integer, so we need to floor it. And to do that, we'll use math.floor. And then we'll add the semicolon there. And then we'll compare that to the previous the result of the previous calculation in the for loop. So we need to create an imaginary first item. So we'll call that prev item, and we'll make that equal to 0. So var y will be equal to x minus the previous item. And then we'll make the previous item equal to x. And then finally, we need to rotate all the numbers in the list. So we'll create a new variable called index, and we'll use a ternary operator. So that means, so you've got a test statement, so which will be true or false, and then if it's true, we'll do something, and if it's false, we'll do something else, and those options will be separated by a colon. So the test statement will be is this step count, is it the final one? So is the step count equal to the number of steps? If yes, it will be 0. Otherwise, it will be I. So basically all that's doing is we're saying step 8 equals 0. Otherwise, step 1 equals 1, step 2 equals 2, step 3 equals 3, etc., etc. And then if we have a rotation value of something different to 0, we can just say the index equals the index plus the rotation, and then we'll take the modulo of that. So the remainder of the division of that with the number of steps. So it will always, that variable indx will always be between 0 and the number of steps. And then finally, we'll assign assign y to that storage location in variable a. So a at the index will be equal to y. And finally, we'll output that. So outlet 0 will output the list A. Save that, close it down, press compile, and observe what's coming out of the JavaScript object. 8. So 1 0 0 1 0 0 1 0. Perfect. So I've got this list of 1s and 0s. How do I make rhythms from it? So I'll need a metro object, and I'll initialize that with an argument of 200. I'll create a toggle to turn that on and off, and I'll create a number box to set the rate, set the period of that metro object. I'll need to get some MIDI notes. So I'll have a MIDI out, MIDI format. I'll need something to make the notes. So let's create all the notes at with a velocity of 100 and a duration of 500 milliseconds. I'll join those pitches and velocities like so, and connect that to the MIDI format box. And we only want to output a note if it's a 1. So to make sure we only do that if it's a 1, we'll use the cell 1. So if it's a 1, output 60. So we'll need a counter to count from 1 to the number of steps. And we'll count the bangs, which are output from the metro object. And we'll take the steps from up here, send it to the count maximum there. And then we're going to need to use the counter to count each element of this list here. So we'll send this list to a ZL nth object, which starts counting from 1. So this is the first element, that's the second, the third. So index 1, index 2, index 3. So this counter is a cold inlet. It goes to the cold inlet of the ZL nth. And this, it will only output something once the list is input again. So we'll use a trigger object actually. So we'll do trigger bang integer. So the integer will go to the cold inlet of the ZL nth, and then the bang will go to this list. So the list will be banged out after the index to read from has been output. So let's see what that looks like in action. We've got, let's put 200 there to be safe. 10, yep, good, okay. So let's just send that to the select object. So hopefully you should be able to hear that. Cool, so I'll turn that off. Yeah, so that's what we want. So how do we derive pitch information from these lists of 1s and 0s? Well, if we go back to our slide, so we've got 12 steps, 7 hits, and rotation 0. If we imagine that each note, or each index in the list of 1s and 0s, corresponds to a MIDI note. So C is element 1 of the list, D flat is element 2, but we start at 0, so it's 0, 1, 2, 3, 4, etc. And then the 1 means that we take that note, and the 0 means we ignore that note. So if we take the C, the D, the E, the F sharp, the G, the A, and the B, we're left with these notes, which is the Lydian mode. So how do we do that in Max? Well, there's an object which takes a list and then successively outputs pairs of numbers, and the first element of the pair is the index, and the second note is the value, which in this case is going to be a 1 or a 0. So we can use a list funnel, and then we can say if the second element of that pair is equal to 1, then we'll output the index. We can just send it the list. And then we need to group that into a list which is going to be the same size as the number of hits. Now let's take a look at what we have there. So first we need to just make sure it knows the number of hits. And we'll bang this list here. And we've got 0, 2, 4, 6, 7, 9, and 11. Now if we offset all of these list numbers by 60, you might even know these MIDI note names. So 60 is normally C3 on the MIDI keyboard, 62 is D, 64 is E, 66 is F sharp, etc. So yeah, we've got the Lydian mode here. But how do computers convert MIDI notes to frequencies? Well, to do this, there's some slightly tricky maths involved. When we go up an octave, we are essentially multiplying our current frequency by 2. So if we're playing an A at 220 Hertz and we go up an octave, we'll now be playing at 440 Hertz. If in 12-tone equal temperament we go up 1 semitone, we are essentially multiplying our frequency by 2 to the power of 1 over 12. So let's just write this in a comment. So our current frequency is multiplied by 2 to the power of the number of semitones we go up divided by 12. So unfortunately we can't use that indices operator in Max. We have to do it like so. So we use pow, and then so 2 to the power of, and then semitones divided by 12. Okay, so in order to do this, to perform this calculation on a list of numbers, we've got to use Vexpera. And our current freak will just basically just choose a random number. So I'll just choose number 10. I think normal MIDI to frequency converters use like 8.7 something as the base frequency. So we'll do that. So we'll just use 10 for now, times pow 2, and then we'll take every element in the list. We need the float because we need this to be an exact number, and we'll put a dot after the 12 so it stays as a float. And we'll see what's coming out of there, and that should be index 1. Let's see what numbers we have here. So if I type in 320 to this try object, and bang this here, so that's my bass note. And then the next one is 359.187. It should be a tone above. Yeah. And then 403. Well, I should do 403.17. And 452.54. That's the sharp fourth. And then 479.458. Yeah, so that's the fifth above. It's in equal temperament. The fifth is slightly flat. So if we lived in an ideal world, we'd to make a fifth, we'd be multiplying our current frequency by 1.5. But using this system of 2 to the power of 7 over 12 for a fifth, we're actually multiplying by 1.49 something. So it's not quite exact. And this is why some people like to use alternative temperaments. So let's use this counter to go from one index of the list to another. So we could use ZL mth, and we'll take this number from the list. So the counter will be our index from the list. We'll need to use the number of steps here, and -1 from there, and I'll just change that back to 7. And then every time that goes, we'll need to times it by there. And I'll just get rid of this, bypass that. Okay. So I've just realized I should have had the counter counting from 0. So now when I press play, we hear the Lydian mode. And then, sorry, at the different rotations, we can hear the different sort of classical modes. And if we change the number of hits to 5, we've got the pentatonic. In different rotations. And if we change the number of hits to 6, we've got the whole tone scale. And the rotation just changes the transposition, but there are only 2 transpositions. And if we change it to 4 hits, we've got the diminished 7th. Now we could actually change this 12. We don't need to divide the scale into 12. We could use another value to divide that by. And we'd have to make this vexpert object a... we'd need to turn on scalar mode. So we'll put on scalar mode. And we can send that the number of steps. So we could actually use sort of 13 tone equal temperament, or I don't know, 1,000 tone equal temperament, and yeah, see what you come up with. Could be interesting. I'll change that to 20. Thanks for watching. I hope this video has been of some use to you and that you find some creative ways to use what you've learned from this. And feel free to get in touch if you have any more questions or thoughts. And please like this video and subscribe to my channel. Thanks.